Get started. I'm Carl Dierking, satellite liaison and meteorologist for GINA, the Geographic Information Network of Alaska, and the University of Alaska Fairbanks. And this is the part of the GINA team. GINA is a direct broadcast data provider. That means we collect satellite data and provide products from it, which I'll explain a little more later. Prior to my working with GINA, I worked for the National Weather Service, where we made extensive use of satellite data to help us monitor weather hazards that were occurring that would affect the population. And so using that experience to show the value of satellite products to the general population. GINA is a strong supporter of the GLOBE program. It's great to encourage educators and students to learn more about environmental science through gathering observations and actually to see the value of those observations being used by the weather community. I want to talk about the satellite products that we use to look at weather, but before I do, I want to talk a little about the different orbital strategies that are used for satellites. There's two different main orbits. One is called geostationary, where a satellite is located at about the equator, but it orbits the Earth at the same speed that the Earth turns, which means that it has the same view of the Earth continuously. And with geostationary, it's a great tool for taking high frequency images of the clouds and weather and converting them into animations, following what's going on. It's a great method for observing severe weather. But it has one issue in that when you're looking very far to the north, it's at the very edge of the view because it's situated over the equator, and so the north image gets stretched. There's a lot of parallax problems, and so for that, the secondary type of satellite is a polar orbiting satellite. It orbits from pole to pole. And with each orbit, the Earth, of course, is rotating. So with each orbit, it passes over a new section of the Earth. And as it does, it's recording this data and then can convert that into a full global observation twice per day, once as it's going from the North Pole to the South Pole, and once as it's going from the South Pole to the North Pole. So with polar orbiting satellites, you get a full view of the Earth for certain features twice per day. That's great, but because this data is recorded, there's two ways that what the satellite sees is downlinked to the ground so that people can see what the satellite sees. One is this recorded data is stored, and at every half orbit, when it passes over the North or South Pole, it dumps that data to special stations that are receiving this recorded satellite data. One is in a place called Svalbard, Norway, and the other is at McMurdo Station in Antarctica. And for this, the recorded data is stored and then produced into products. That's good for getting these full views of the whole Earth, but there is going to be some delay because it takes about 90 minutes for the polar satellite to orbit the Earth. And so that means 45 minutes from when it may be passing over Alaska to when that data is actually dumped to these antennas at, for example, McMurdo in Antarctica. So for that reason, there's a second method for receiving this data. It's called direct broadcast. And this uses a separate transmitter where what the satellite sees is broadcast immediately. as it scans the Earth. And if you have the right antennas and you're within range of that satellite, you can receive what the satellite sees immediately. And that's what GINA has. We have 3 antennas currently. We can receive the data as the satellites are in range and convert that into products. The reason that's important is that now you can immediately turn that satellite data into products that can help monitor hazards that affect Alaska. And Alaska has a lot of hazards. These are just some of the more significant ones. In red, I've highlighted just the ones that might be a problem in the winter. And so there's all kinds of hazards that are important for us to monitor. And with direct broadcast, we can get timely information to help us see how those hazards are changing. And we have an advantage being in the far north in that because the satellites orbit from pole to pole, they pass over the same area in the polar region more frequently. The graphic on the right shows the number of passes for 3 particular satellites for each day. And the colors represent passes per day. You can see there's kind of a maximum just above the northern coast of Alaska, but even over the interior of Alaska, there's still, for just those 3 satellites, there's about 18 passes, 16 to 20 per day. And then GINA currently receives 9 satellites. So we get a lot of information from these satellites each day. And from that, we can generate a number of products. There's a ton of different products for different hazards that we produce. But what we're particularly interested for this project is the Alaska snowfall rate. This is just focused on snowfall, and I'll talk specifically about what this product is. If you look at a typical satellite view of the clouds, this is what a meteorologist would maybe be looking at in the cloud pattern. And after looking at it for a while, you can get used to the type of patterns you're looking at. So as I point out, this is in the Gulf of Alaska and Southeast Alaska. You can see the speckled pattern that the red arrow points to, which is typical of a shower pattern. And because the temperatures are cold, we know that it's snow showers. And then going from the lower center to the upper right part of this picture, you can see a more continuous layer of clouds. And we know from temperatures where the red arrow is in the upper right is more steady snow, and in the lower right is more steady rain. Well, we have satellite products that can interpret that as well. And in blue, the blue shades is this particular product, the snowfall rate product, where it can tell us that there's snow occurring over the Gulf of Alaska and Southeast Alaska, more in the shower pattern because it's a little more speckled, and then more steady in the upper right. We also have a product that can do rain that's showing up in the pink shades, but that's not a product that we're going to be working with for this project, but just to give you an idea of what these satellite products can do. So the image that I showed you earlier was from a type of workstation that meteorologists would use at the National Weather Service, but we also can make this information available to the general public. This is an example of the snowfall rate page provided by NOAA and the University of Maryland. They generate this product, and this link is how you can get access to it. I'm going to click on it here, and we'll see it real time right now. So for some reason right now, I don't see any images, but let me step backward a day. if you click on this box, you can select the day that you want to look at. And here we have the snowfall rate product that you can view, and through this application you can pan around, you can zoom in with the scroll bar or with these plus and minus. If you click on this box, you can turn on the county view, and as you zoom in, more and more cities are available to see where your city might be located. If you pan over to an area where you see actual snow reported, if you click on that area, it will give you the snowfall rate in inches per hour. One thing I need to point out is that the snowfall rate on this application is the liquid equivalent. There's a lot of reasons, there's a lot of factors that change the accumulation of snowfall at the surface. So what the satellite sees is what's going on in the cloud. It can tell that it's frozen precipitation, and it can tell the amount of water in that frozen precipitation, but it can't tell you how that's going to accumulate on the surface. So that's where surface observations are important, because we know the water content, or we know an estimate of the water content from the satellite. But the surface observations are important to tell us how that is accumulating on the ground. So in this case, we're looking at 0.17 inches per hour. If you think of snow rain ratios, say if you have a 10-to-1 ratio of snow to rain, 0.17 inches per hour would be equal to 1.7 inches of snow. And if that continued for several hours, you'd have a significant amount of snow. So the amount of liquid in the cloud is important to determine how much snow is going to accumulate at the ground.
Great. And Carl, while you're on that page, I see that it says METOP B at the top, and you can click on that and look at other satellites. Could you explain? And then on the lower part, you have all satellites selected. Right. How would people see what different satellites are overpassing?
Yes, there are, like I said, there's a number of satellites, and the default is to display them all. And in general, it's probably most useful just to look at them all. But if you really wanted to see specific satellites, you can toggle them on and off here on this page. I'll return to this presentation and go back a few slides. Well, there are two links here that can provide some information about what satellites you might be expecting to see. This link will give you up-to-date information on what satellites are in the area, and you can start clicking on, for example, this METOP satellite. And maybe we'll turn on NOAA 20. But that's one way of looking at what satellites are passing overhead at the time. It gives you a color showing the swath and the coverage of that satellite. Another page that GINA provides shows a view of the expected satellite coverage within range of GINA's antennas. And it gives the satellite and when the pass is expected to start.
Great. I also want to point out to folks who are watching this that the Globe Observer app under the Clouds tool also has satellites as well, that you can get notifications when a satellite is overhead.
Okay, so Now, getting back to the this liquid equivalent, there's a big difference in what happens on the ground depending on conditions at the surface. Wet snow versus dry snow can have a big difference in impacts. Dry snow is fluffy and easy to remove. It blows easily, so that could be a problem with visibility if the winds are high, and can produce more drifting. Obviously good for skiing, like if especially people that like powder. Not so good for making snowmen. Wet snow has significant impacts for removal. It's heavy and difficult to move. It's hard to shovel. Driving can be really difficult in heavy wet snow. Great for snowmen and snowballs. But just to give you an idea, the ratio of wet snow or snow to rain can be significant. And as we're looking at that liquid equivalent prediction that the satellite sees, the ratio is what we would use to determine how much of that liquid will accumulate on the ground. And again, a difference of 7 to 1 can make a big difference on the ground versus 15 to 1. The weight of snow, for example, in a shovel, dry snow might only be 5 pounds, wet snow up to 20 pounds. So these are big differences, and so that water content of the snow is an important factor in this. The snowfall rate product is created with machine learning. It takes a lot of observations, compares them with certain meteorological data, and uses machine learning. It's a subset of artificial intelligence, really, that comes up with a algorithm for estimating, based on what the satellite sees, how much water is going to fall as frozen precipitation. It's important to have ground truth, these observations from the ground, so that we can feed that back into the process and do additional learning or retraining to improve these algorithms and make them better. So the more observations that we have that we can apply to the algorithms, the better the estimates are going to be from space. So we're asking a little more from this, the intensive observing period of GLOBE. We're really looking for as many observations as we can get, even hourly observations of measuring the snow change on the snowboard each hour. Not to clear the board, but to just measure the change of snow each hour. And then once a day to do a liquid equivalent or a snow water equivalent, so that we can determine how well that water content matched what the satellite was observing. So just a summary, can't express how important these snow observations are. It's important for warnings, for transportation, for many things. Alaska is a big place, and we don't have a lot of observations at the surface. So this is an important project that can be applied and actually make the tools that we use better. The snowfall rate is one of those tools, and that can help fill those observation gaps where we can see by satellite in areas that we don't necessarily have people. But one thing is that the snowfall rate reports the liquid equivalent of frozen precipitation, so we can use these local observations and measurements of the accumulation of snow as well as the snow water equivalent to help improve the snowfall rate. And that's it.
Well, that's awesome. Thank you so much, Carl. I'm very excited that across Alaska, we have some educators and community members and students who will be going outside. Again, we are asking for people to place a snowboard, which I will be providing to folks in Alaska, and then also doing a video demonstration of how this is done. And on that snowboard, snow will fall on it. Now, it's not like the snowboard that you use to go on a chairlift and snowboard down. It is a square board that has been painted white so that it can reflect light back and not melt snow that accumulates on it. And then you place a pink flag, like a globe flag, something that you know where the snowboard is located, and go and use a meter stick to measure in millimeters. So those are the units that Globe will use. Often it'll be easy for people to see 10 centimeters, 1, 2, 3, 4, 5 centimeters, but we are asking for millimeters. And students will be able to look very closely on the millimeters on the snowboard itself and measure that. But then when they melt the snow, when they collect it in this outer rain gauge tube inverted on the snowboard, and collect it into a jar or a bag of some sort that's covered, then they'll take that inside and then they will melt it. And we do have a video demonstration of how this is done. And they will pour the melted water in this funnel and into this inner tube, which is graduated to be read also millimeters of liquid equivalent of snow. So the millimeters of snow that people collect on the snowboard, that data will be then shared with Carl and his team to compare with the snowfall rate satellite data product.